Despite these promising discoveries, the Fermi Paradox remains unresolved. Although there seems to be an abundance of habitable planets, no clear evidence of intelligent life has emerged. Research has shown that life can thrive in extreme environments, raising the possibility that microbial life, Fermi Paradox. Picture for a moment the night sky above you. Those twinkling stars aren't just distant suns, but potential homes for other life forms. Considering the high probability of extraterrestrial civilizations existing in the Milky Way galaxy, why haven't we detected any signs of them? This is the essence of the Fermi Paradox, a question that sits at the intersection of science and philosophy. The Fermi Paradox highlights the apparent contradiction between the high likelihood of extraterrestrial life and the complete lack of evidence or contact with such civilizations. Named after Nobel Prize-winning physicist Enrico Fermi, who famously asked, "Where is everybody?" during a casual lunchtime conversation in 1950, the paradox underscores the puzzling silence of the cosmos. It begins in the vast, seemingly endless cosmos, where countless stars shine and galaxies spiral in a grand cosmic dance. Humanity has long pondered a profound question: are we alone? This inquiry, as ancient as human curiosity itself, has fueled imaginations, driven scientific research, and inspired countless works of fiction. At the heart of this pursuit lies one of the most perplexing mysteries in the search for extraterrestrial life: the Fermi Paradox. Our solar system, approximately 4.5 billion years old, is relatively young compared to the universe, which is around 13.8 billion years old. Given this, and assuming that interstellar travel is achievable given enough time, Earth should have already been visited by extraterrestrial civilizations. Fermi recognized that any civilization with even a modest level of rocket technology and a strong enough imperial drive could theoretically colonize the entire galaxy within a few tens of millions of years, a mere blink of an eye on a cosmic scale. And yet, no such presence has been observed, leaving astrobiologists and scientists puzzled for decades. In 1975, Michael Hart, in his article, An Explanation for the Absence of Extraterrestrials on Earth, suggested that the lack of evidence might be best explained by the possibility that advanced civilizations simply do not exist in our galaxy. He outlined 4 potential explanations. Aliens never visited Earth due to physical limitations that make space travel impossible, whether related to astronomy, biology, or engineering. Aliens deliberately chose never to visit us. Advanced civilizations outside Earth emerged too recently to have reached us. Aliens may have visited Earth in the past, but we have not observed or recognized them. Building on Hart's argument, in 1980, Frank Tipler, a professor of physics at Tulane University, proposed that the absence of evidence for interstellar machinery suggests that we might be the only intelligent beings in the galaxy. Tipler theorized that self-replicating artificial intelligence could, in principle, spread from one star system to another, creating copies of itself along the way. The lack of such technology further reinforced his belief that intelligent extraterrestrial life may not exist. Today, the question of extraterrestrial intelligence continues to captivate scientists. The discovery of exoplanets, planets orbiting stars beyond our solar system, has intensified speculation. The observable universe is vast, spanning approximately 90 billion light-years, and is about 13.8 billion years old. When Fermi made his famous remark, the only known planets were those in our solar system. However, in 1992, astronomers detected planets orbiting a pulsar, and a few years later, the first exoplanet around a sun-like star was confirmed. Now, over 5,000 exoplanets have been discovered, with more being identified every year. This vast number suggests that life could be widespread throughout the cosmos. Advances in telescope technology will soon allow scientists to analyze the chemical compositions of some nearby exoplanet atmospheres. The closest known exoplanet, Proxima b, is about 4.2 light-years away, roughly 25 trillion miles from Earth. Assessing the habitability of these planets requires more than just finding water. Factors such as the activity of the host star and the planet's atmospheric composition are also critical. It exists on planets or moons within our own solar system, such as Mars, Europa, or Enceladus. However, the Fermi Paradox specifically concerns intelligent life capable of interstellar communication or travel. To resolve the paradox, we need to determine how often life evolves to an advanced level of intelligence and whether such civilizations would have the desire to communicate or travel among the stars. The core premise of the Fermi Paradox remains a topic of debate among researchers. Some argue that the lack of contact suggests we are alone, while others believe the vast distances and immense timescales involved in space travel and communication create significant barriers. Modern researchers studying exoplanets often use the Seeger equation, an update to the Drake equation, which focuses on detecting life that has altered a planet's atmosphere. The search for extraterrestrial intelligence, commonly known as SETI, has not yet identified signals from advanced civilizations, shifting the focus toward detecting signs of simpler life forms. As our understanding of exoplanets grows, we may come closer to answering the questions posed by the Fermi Paradox. With the staggering number of stars in the Milky Way and the increasing knowledge of habitable conditions, scientists continue to refine their estimates of the likelihood of intelligent life elsewhere. Researchers have proposed several hypotheses to explain the paradox. One of the most prominent is the Great Filter theory, which suggests that there is a critical stage in the development of life that is exceptionally difficult to overcome. The Great Filter could be behind us, meaning the emergence of intelligent life is exceedingly rare, or it could lie ahead, posing a major challenge, or even an existential threat to advanced civilizations. Another possibility is the zoo hypothesis, which suggests that extraterrestrial civilizations may intentionally avoid contact with us, much like how humans observe animals in a zoo without interfering. This could be due to ethical considerations, a form of cosmic quarantine, or simply because they find us uninteresting. There is also the simulation hypothesis, which speculates that our reality might be a simulated environment created by a more advanced civilization. If this were the case, the absence of extraterrestrial contact could be a programmed feature of our simulation. Additionally, some scientists propose that advanced civilizations might be communicating using technologies beyond our current understanding, such as neutrinos or gravitational waves, methods that we have yet to detect or interpret. Alternatively, these civilizations might have turned their focus inward, exploring virtual realities or other dimensions rather than expanding outward into space. The Fermi Paradox remains one of the most intriguing mysteries of modern science. Whether the solution lies in a cosmic great filter, an advanced alien civilization's deliberate silence, or a limitation in our own technology and understanding, humanity's quest to uncover the truth continues. The universe is vast, and as our tools and knowledge evolve, we may one day find the answer to one of the most profound questions. Are we truly alone? These various hypotheses underscore the complexity of the Fermi Paradox and the numerous ways we might eventually solve it. Each theory offers a distinct perspective on the silence of the cosmos, compelling us to broaden our scientific and philosophical horizons in our search for answers. Imagine holding 6 tons of sand, with each grain symbolizing a star in our galaxy. While it may seem logical to assume that at least one grain contains uranium, we don't search for uranium on the beach because it would dissolve in water and be washed away. Similarly, just because there are countless stars, it does not necessarily mean that intelligent life must exist around one of them. Current experiments and missions strive to comprehend the conditions on exoplanets, the likelihood of life, and the potential for technological civilizations to emerge. These efforts will assist us in better evaluating the probability of discovering intelligent life and the possibility of its expansion throughout the galaxy. The Fermi Paradox remains one of the most intriguing and difficult puzzles in the quest for extraterrestrial life. As we contemplate the silence of the cosmos, we delve deeper into the theories that might unravel this grand mystery. In our next section, we will examine the Drake equation, a scientific formula designed to estimate the number of active, communicative extraterrestrial civilizations in our galaxy. The Drake equation. We have explored the Fermi Paradox and its profound question: where is everybody? Now, let's delve into another crucial theory in our search for extraterrestrial life, the Drake equation. This equation aids scientists in estimating the number of active, communicative extraterrestrial civilizations in the Milky Way galaxy. Astrophysicist Frank Drake formulated the Drake equation in 1961. It does not directly answer whether aliens exist, but rather presents a probabilistic formula that highlights the factors we must consider. Think of it as a structured way to organize our thoughts about the search for extraterrestrial life. At its core, the Drake equation incorporates several variables, including the rate of star formation in our galaxy, the fraction of those stars with planetary systems, and the number of planets that might sustain life as we understand it. It also accounts for the fraction of planets where life actually arises, the fraction that evolves into intelligent life, the fraction of intelligent civilizations that develop communication technologies, and finally, the duration such civilizations remain detectable. Now, let's break down each component of the equation. First, we have R star, which represents the average rate of star formation per year in our galaxy. Recent research estimates that approximately 1 to 3 stars form in the Milky Way annually. This rate serves as the foundation for all the subsequent factors. Next, we consider FP, the fraction of those stars that have planetary systems. With the advent of advanced telescopes like Kepler, we have discovered that planets are quite prevalent. In fact, it is estimated that nearly every star hosts at least one planet, making FP close to 1. Then, there is NE, the number of planets per star that could potentially support life. This is where the concept of the habitable zone becomes crucial. The region around a star where conditions may be just right for liquid water, a fundamental ingredient for life as we know it. Studies suggest that there could be between 0.4 to 1.2 potentially habitable planets per star. The next factor is FL, the fraction of these habitable planets where life actually emerges. This remains one of the most uncertain aspects of the equation, as Earth is our only known example of life. If life is common, FL could approach 1, but if it is rare, it could be significantly lower. Following this, FI represents the fraction of planets with life, where intelligent life evolves. On Earth, it took roughly 3.5 billion years for simple organisms to evolve into intelligent beings capable of developing technology. The forces driving this evolution remain largely unknown, adding another layer of uncertainty. The next variable, FC, represents the fraction of intelligent civilizations that develop technology enabling interstellar communication. This includes technologies such as radio signals that can traverse space. On Earth, humans have been broadcasting radio waves for only about a century, an incredibly brief period in geological terms. Finally, L stands for the duration such civilizations remain detectable. This is perhaps the most difficult factor to determine. If civilizations tend to destroy themselves or lose interest in communication quickly, L could be very short. However, if they persist and continue transmitting signals for millions of years, L could be considerably long. Bringing all these elements together, the Drake equation appears as follows. N equals R, star times FP, times NE times FL times FI times FC times L, where N represents the number of civilizations in our galaxy with which we might establish communication. While the equation itself is simple, determining accurate values for each variable remains the challenge. As our knowledge of the cosmos expands, so too will our estimates for these variables. Recent progress in planetary research has provided valuable data to refine the Drake equation. For example, we now understand that roughly 1/5 of stars host planets within their habitable zones, where conditions might allow for liquid water. This improves our estimation of NE, thereby increasing confidence in our calculations. Astrobiologists Adam Frank and Woodruff Sullivan have further extended the Drake equation by introducing what they call the archaeological version of the equation. Instead of focusing solely on the present, they consider the entire history of the universe. They calculate the probability of technological civilizations arising at any point in time throughout the cosmos, not just those that currently exist. This broader approach shifts the question from how many civilizations are out there right now to how many civilizations have ever existed. This perspective helps address uncertainties regarding the longevity of civilizations and their detectability over time. Frank and Sullivan's findings suggest that if the probability of a civilization emerging on a habitable planet is greater than 1 in 10 billion trillion, then we are likely not the first advanced civilization. This minuscule probability implies that what occurred on Earth, the emergence of a technological species, has likely happened multiple times throughout cosmic history. Their research also emphasizes the impact of recent exoplanet discoveries. With over 5,000 confirmed exoplanets, many residing within habitable zones, the chances of life existing elsewhere seem increasingly plausible. These discoveries help refine estimates for FP and NE, reducing some of the uncertainties within the Drake equation. However, one significant factor remains uncertain: the longevity of civilizations. Human civilization has only possessed advanced technology for a few thousand years, a mere blink in the cosmic timeline. Whether other civilizations endure for longer periods or face early extinction remains unknown. Understanding this variable is essential for refining our estimates and answering the profound questions raised by the Drake equation. As we continue to explore the universe, advancements in telescope technology and space missions will provide additional data, helping us gain deeper insight into the factors influencing the Drake equation. The search for extraterrestrial life is not merely a scientific inquiry. It is a pursuit to understand our place in the cosmos and the possibility of life beyond our planet. The Drake equation serves as a guiding framework for this exploration, aiding scientists in their quest for answers. While we do not yet possess all the answers, every new discovery brings us one step closer to understanding whether we are truly alone in the universe. The dark forest theory. We have examined the Fermi Paradox and the Drake equation. But what if the reason behind our silence in the universe is far more unsettling? Enter the dark forest theory, a concept that presents a chilling explanation for why we have yet to encounter extraterrestrial intelligence. The Fermi Paradox has baffled astronomers for decades. If the universe is nearly 14 billion years old, why have we not found any signs of interstellar civilizations? Why have they neither visited nor communicated with us? The dark forest theory offers a possible explanation. They are in hiding. According to this theory, the reason we do not observe these alien civilizations is that they are all concealing themselves, fearing potential threats from other intelligent beings. This idea has gained traction, especially due to its portrayal in the Netflix series The Three-Body Problem, based on the literary trilogy by Liu Cixin. But what makes this theory so compelling? And could it genuinely explain the silence of the cosmos? The dark forest theory suggests that the universe resembles a vast, dark forest, where each civilization is akin to a hunter, armed, cautious, and alert. The primary rule in this forest is to avoid detection. Just as a hunter moves silently to prevent revealing their location to potential dangers, extraterrestrial civilizations may choose to remain hidden to avoid being discovered and potentially annihilated by more advanced civilizations. In Liu's book, the universe is portrayed as a place where any sign of life is a potential threat. If a civilization reveals its location, it risks being eliminated by another, more powerful civilization. This is because, in the immense and mysterious dark forest of the cosmos, no one can be certain of the intentions of others. The safest strategy, therefore, is to remain silent and hidden. Unlike humanity, which has been transmitting radio signals into space for over a century, these alien civilizations may have concluded that it is too dangerous to announce their presence. This self-imposed silence serves as a survival tactic in a universe where any contact could result in catastrophic consequences. However, the plausibility of this theory is widely debated among experts. While some extraterrestrial intelligences might opt to conceal themselves, it seems improbable that all would reach the same conclusion. Humanity itself provides a clear example of behavioral diversity. We have groups that are aggressive, peaceful, inquisitive, and reclusive. If such diversity exists on Earth, it likely exists elsewhere in the universe. Astrophysicist Moya McTeer notes that even among human cultures, behaviors are not uniform. It is highly unlikely that every alien civilization would act in perfect unison, all choosing the same fear-driven strategy of hiding. If even one civilization decided to make itself known, it would illuminate the dark forest, allowing us to see them. Nevertheless, considering that we have no concrete evidence of extraterrestrial intelligences, it remains a possibility that they are all in hiding. Perhaps there truly is an immense danger lurking in the depths of space, one that humanity has yet to recognize. The Fermi Paradox. First articulated by physicist Enrico Fermi, the Fermi Paradox revolves around a fundamental question. If there are so many potential civilizations in the universe, why have we not seen any evidence of them? The paradox highlights the contradiction between the high probability of extraterrestrial civilizations and the absence of evidence or contact with them. The idea that spacefaring aliens may be deliberately avoiding detection has been a recurring theme in science fiction for decades. In his 2008 book, Liu Cixin gave this hypothesis a memorable name: the dark forest. He described the universe as a dark and ominous forest, where each alien civilization is like a wary, armed hunter, treading cautiously. If that hunter encounters another form of life, be it another hunter, an angel, a demon, a fragile newborn, an elderly being, a fairy, or a demigod, there is only one action they can take: fire and eliminate them. In this forest, hell is other people. Fear can offer evolutionary advantages. On Earth, humans have evolved to be cautious. We instinctively flinch at unexpected noises in the night. While most of these instances turn out to be harmless, the one time the sound signals a real threat, our caution could save our lives. In the vast and unknown expanse of the universe, this instinct for self-preservation could be even more pronounced. Seth Shostak, a senior astronomer at the Search for Extraterrestrial Intelligence, SETI, in California, suggests that aggression can provide survival benefits. Eliminating potential competition preemptively can help secure resources and ensure safety. Throughout human history, there are countless examples of this behavior, from ancient wars to modern conflicts. Humanity has already revealed its presence. However, Earth has already announced its presence to the universe. In 1974, the Arecibo message, a radio transmission containing information about Earth and humanity, was beamed toward the globular star cluster M13. This binary message was designed as an attempt to communicate with potentially intelligent extraterrestrial civilizations. If any such civilizations exist within a 25,000 light-year radius, they may have received our message. Despite our willingness to broadcast our existence, there are significant challenges to the dark forest theory. One major issue is that it is incredibly difficult to conceal a technologically advanced civilization. Long before humanity deliberately began searching for extraterrestrial intelligences, our daily communications had already been leaking radio signals into space. While these signals weaken over vast distances, they could still be detected by nearby alien societies. Even if an extraterrestrial civilization attempted to hide itself, it may not be technologically advanced enough to do so effectively. Some alien societies might have succeeded in eliminating all detectable emissions, but others may still be unintentionally revealing themselves, just as early humans attempting to hide would do so quite differently from an advanced species like the Klingons. The forest analogy also begins to break down when considering the actual scale of the universe, or even just our own galaxy. While a forest may seem vast and endless in the dark, it is insignificant compared to the enormity of space. There could indeed be hostile extraterrestrial beings out there, but the sheer distances between civilizations may make encounters extraordinarily rare. Shostak suggests that while extraterrestrial civilizations may exist, the vast distances between them are likely incomprehensibly large. This means the idea of them feeling compelled to launch preemptive attacks on one another seems unlikely. Even if they harbored fear, the immense separation would eliminate the need for competition over resources, as each civilization would have nearly unlimited access to planets, asteroids, and even stars. Furthermore, Earth, by universal standards, is a relatively young, noisy, and technologically vulnerable society. This inherently implies that if extraterrestrial intelligent beings, ETI, exist, not all of them can be inherently aggressive. Researcher Karim Jabari from the Institute for Future Studies in Stockholm, Sweden, points out that if multiple civilizations are out there, and some possess the ability to destroy us, we must question why this has not yet occurred. He suggests the possibility of a galactic empire that suppresses hostilities, or perhaps the logistical difficulty of attacking across interstellar distances prevents conflict. Another theory Jabari has proposed in a recent paper is that extraterrestrial intelligences have all arrived at the same rational conclusion. They continue to exist because other advanced alien societies have consciously chosen not to annihilate them, possibly in hopes of engaging in mutually beneficial communication. Jabari asserts that there is no rationale for initiating a preemptive strike against extraterrestrial beings, and if they are intelligent, they may hold the same perspective about us. Assuming that all extraterrestrial intelligences share the human instinct of fearing the unknown is a significant presumption. McTeer argues that the dark forest theory is one of the less convincing explanations for the Fermi Paradox, since it is based on several anthropocentric assumptions that may not be valid. While fear is powerful, so is curiosity. This does not mean the dark forest hypothesis should be dismissed outright. However, addressing its weaknesses necessitates heightening the level of fear it assumes. The most alarming possibility, according to Crawford, is that civilizations choosing to remain hidden may have valid reasons. Suppose that at some point in the galaxy's history, a technologically advanced civilization resolved to destroy any planets displaying signs of life or technological progress. If extermination for the sake of extermination was the primary objective, then the dark forest theory becomes more credible. Crawford suggests that if such an entity has been operating throughout the galaxy's history, it would indeed provide a plausible explanation for the Fermi Paradox. Alternatively, the apparent silence of our cosmic neighborhood might be due to the extreme rarity of life's emergence in the first place. It is also possible that extraterrestrial societies tend to self-destruct once they reach a technological threshold, such as the development of atomic weapons. Another possibility is even more chilling. Perhaps we do not detect extraterrestrials because a predatory force is systematically eradicating life from star to star. This terrifying concept presents a haunting justification for our solitude in the universe. However, the notion of a vast, universe-wide game of hide-and-seek may not withstand closer examination. Even if some civilizations remain concealed, others may prioritize curiosity or have alternative survival strategies. The diversity of human cultural behaviors suggests that not all intelligent entities would choose silence as a survival mechanism. Another major challenge to the dark forest theory is the sheer scale of space itself. The distances between stars and galaxies are so enormous that even if advanced civilizations exist, they may be too far apart to interact, let alone pose a threat to each other. The concept of preemptive strikes or intergalactic warfare appears more fitting for a science fiction narrative than a probable reality. Furthermore, highly advanced civilizations may have developed technologies far beyond our comprehension. They could be communicating through methods we cannot yet detect, such as neutrino signals or other exotic particles. Our current approaches to searching for extraterrestrial intelligence may simply be too primitive to identify these sophisticated forms of communication. In summary, while the dark forest theory presents a compelling and unsettling explanation for the Fermi Paradox, it is only one of many potential answers. The silence of the universe could stem from numerous factors, ranging from the extreme rarity of life to the immense interstellar distances separating civilizations. As humanity advances technologically and continues to explore the cosmos, we may eventually uncover the true reason behind this cosmic quietude. Until then, the dark forest hypothesis remains an intriguing yet disquieting possibility. The zoo hypothesis. As we strive to understand why we have yet to encounter extraterrestrial life, various theories emerge to explain this enigma. One such idea is the zoo hypothesis, which offers a unique perspective on the Fermi Paradox. This theory posits that advanced extraterrestrial civilizations are deliberately avoiding contact with Earth, allowing humanity to evolve naturally, similar to how humans observe animals in a zoo. The zoo hypothesis was initially proposed to address the apparent absence of extraterrestrial contact, despite the high probability of their existence. It suggests that these advanced civilizations are fully aware of us, but intentionally refrain from interference. This non-interventionist stance ensures that human social and cultural evolution progresses without external influence, preserving the integrity of our natural development. A variant of this hypothesis, proposed by former MIT Haystack Observatory scientist John Allen Ball, is the laboratory hypothesis. This concept envisions Earth as a massive experimental site where extraterrestrials study humanity to understand how civilizations develop and address challenges such as self-destruction, warfare, and environmental crises. Though unsettling, this idea implies that these advanced beings may have altruistic motivations. According to the zoo hypothesis, extraterrestrials might withhold contact until humanity reaches certain milestones in technological, political, or ethical development. For example, once we achieve interstellar travel or demonstrate sustained global peace, they might decide that we are ready for communication. Alternatively, contact might occur when we take the initiative by sending spacecraft to their planets. One fundamental assumption of this hypothesis is that life tends to emerge wherever conditions allow. Given the vast number of exoplanets within habitable zones, it is plausible that many advanced civilizations exist. These civilizations, adhering to the zoo hypothesis, may have a deep respect for the independent evolution of other species. Premature contact could disrupt this natural course, reducing the diversity of evolutionary paths the universe could take. The idea that extraterrestrial civilizations abide by a universal policy of non-interference is conceivable. If the universe lacks a dominant power, random encounters between civilizations might occur. However, a cosmos governed by widely accepted regulations seems more plausible. If all advanced societies follow similar ethical principles, enforcing non-interference becomes easier. This concept resembles the Prime Directive in the Star Trek franchise, where the Federation avoids interfering with less developed cultures. Nonetheless, the idea that all extraterrestrial civilizations share the same motivation is not without challenges. It would only take a single civilization, or even a rogue faction within one, to defy the non-interference rule and make their presence known. The likelihood of such a breach increases with the number of civilizations that exist. However, if all intelligent species evolve similar ethical frameworks through convergent evolution, they might universally adhere to a policy of non-interference, much like how different species on Earth have independently evolved eyesight. Another possibility is that one particularly influential civilization, perhaps the first to achieve advanced status, has set a precedent for others to follow. For the zoo hypothesis to be valid, these civilizations must have overcome significant existential threats, such as self-destruction and resource depletion, leading them to adopt responsible behavior. Otherwise, their chances of surviving long enough to become highly advanced would be slim. Under this perspective, no contact would be feasible until humanity surpasses these challenges and demonstrates its maturity. According to one estimate, humanity may have the ability to test the zoo hypothesis within the next 50 years. As our technology advances, we could eliminate ways in which extraterrestrial civilizations may conceal themselves from us. For instance, improvements in remote sensing technology might enable us to identify artificial structures or signs of technological activity on distant planets. A revised version of the zoo hypothesis incorporates the idea of hegemonic power to account for the Fermi Paradox. The first advanced civilization may have set a precedent with a strict non-interference doctrine, which subsequent civilizations continue to follow. Even if this pioneering civilization has ceased to exist, its influence might endure through inherited traditions or artificial intelligences programmed to uphold the non-interference principle. This would explain how a single doctrine could shape numerous civilizations over millions of years. Despite its intriguing nature, the zoo hypothesis has faced notable criticism. Detractors argue that it would require absolute unanimity among extraterrestrial civilizations, meaning not a single group would deviate from the non-interference agreement. However, History demonstrates that uniformity in behavior is rare, making it improbable that all advanced civilizations would uphold this policy for millions of years without exception. Additionally, some critics contend that the hypothesis is largely speculative and leans more toward philosophical or theological ideas rather than empirical scientific evidence. One possible counterpoint is the idea that extraterrestrial artificial superintelligences dominate space, even in regions inhabited by biological beings. These superintelligences could integrate into a vast interstellar network, discouraging rogue behavior and reinforcing the non-interference principle. The zoo hypothesis has been frequently explored in science fiction. For example, in Star Trek, the Prime Directive prohibits interference with civilizations that are technologically less developed. This theme of non-interference and allowing societies to evolve naturally is central to the series. Similarly, in Arthur C. Clarke's 2001, A Space Odyssey, a lunar beacon activates when humans discover it, possibly signaling humanity's preparedness for contact. Clarke also delves into this concept in Childhood's End, where aliens monitor Earth's progress and reveal themselves only when humanity is on the verge of achieving space travel. More contemporary works have also incorporated the zoo hypothesis. In the strategy game Stellaris, players can observe primitive civilizations without intervening, aligning with the hypothesis's principles. These fictional depictions help us visualize how advanced extraterrestrial civilizations might interact with developing ones and highlight the ethical dilemmas involved. As a compelling explanation for the Fermi Paradox, the zoo hypothesis proposes that advanced civilizations deliberately avoid contact to protect the natural progression of less developed societies. This suggests a profound respect for the diversity of life and the importance of independent growth. Expanding on this idea, we can consider the technological capabilities required for such non-interference. Highly advanced civilizations would likely possess sophisticated surveillance and observation technologies, enabling them to monitor Earth without revealing their presence. They might deploy cloaked satellites, autonomous probes, or other advanced tools to collect data without detection. These devices would allow them to study our technological progress, cultural transformations, and even biological evolution, all without direct engagement. Additionally, these civilizations might adhere to ethical frameworks designed to protect less evolved species. Such principles could stem from a thorough understanding of the repercussions of premature contact. They might recognize that introducing advanced knowledge or technology too soon could destabilize a developing society, disrupting its social structures and hindering its organic progress. By following these ethical guidelines, they ensure that their presence does not inadvertently cause harm. Another factor to consider is the possibility of interstellar communication among extraterrestrial civilizations. They may establish agreements on how to approach emerging civilizations like ours. This coordination could involve shared policies and establish guidelines for non-interference, upheld by an alliance of advanced societies. Such a coalition could function as a regulatory body, ensuring all members adhere to the zoo hypothesis's principles. Furthermore, the zoo hypothesis raises the concept of a galactic quarantine. This idea suggests that advanced civilizations may intentionally isolate developing planets to prevent contamination or unwanted influence. Earth could be part of a designated no-contact zone, maintained by these civilizations to safeguard both our progress and their security. This quarantine would restrict direct interactions until we reach a particular level of technological advancement, ensuring that our societal and scientific evolution occurs naturally. Critics of the zoo hypothesis argue that it heavily depends on assumptions about extraterrestrial behavior and intentions. They highlight that human history is marked by curiosity and exploration, traits that may be common among intelligent beings elsewhere in the universe. If even one civilization decided to break the silence and initiate contact, the entire premise of the hypothesis would collapse. Furthermore, the immense distances between star systems and the extensive timeframes involved would make enforcing coordinated non-interference exceedingly difficult. Despite these challenges, the zoo hypothesis remains a fascinating perspective on the Fermi Paradox. It encourages us to contemplate the ethical dimensions of first contact and the responsibilities of more advanced civilizations. As we continue our search for extraterrestrial life, we must consider the possibility that we are being observed, even if we are currently unable to detect our observers. Ultimately, the zoo hypothesis presents a unique viewpoint on why we have not yet encountered alien life. It suggests that advanced civilizations may intentionally avoid contact to preserve the natural development of younger species. This approach embodies a deep respect for the diversity of life and acknowledges the potential risks of premature exposure to advanced knowledge. While the hypothesis faces significant criticisms and remains speculative, it provides a compelling and thought-provoking explanation for the apparent silence of the cosmos, the Great Filter. As we further explore the mysteries of the universe, we encounter another profound and sobering theory that attempts to explain why we have yet to find evidence of extraterrestrial civilizations. This theory is known as the Great Filter Hypothesis, a concept that could provide crucial insights into the seeming absence of intelligent life in our galaxy. The Fermi Paradox, which we have previously examined, poses a deceptively simple yet perplexing question. Where is everybody? With billions of stars and potentially habitable planets in the Milky Way, why have we not discovered any signs of intelligent life? The Great Filter Hypothesis offers one possible answer, suggesting that there exists a formidable barrier preventing civilizations from advancing to a highly developed stage. The term Great Filter was first introduced by economist Robin Hanson in the late 1990s. He proposed that while life may frequently emerge across the galaxy, there is an exceptionally difficult obstacle that civilizations struggle to overcome. This filter could be a natural event such as an asteroid impact or a consequence of the civilization's own technological advancements, such as nuclear war, play a crucial role in understanding the Great Filter. To comprehend this concept, we must examine the various stages of development that a civilization must go through to achieve interstellar communication and travel. These stages include the formation of a habitable planet, the emergence of simple life, the evolution of complex multicellular organisms, and the development of intelligent life capable of using advanced technology. The Great Filter suggests that at least one of these stages is so improbable that almost no civilization manages to advance beyond it. This concept helps explain why, despite the high probability of extraterrestrial civilizations existing, we have yet to detect any. So, what could the Great Filter be? Let's explore some potential barriers that civilizations might encounter. One possibility is that the Great Filter lies in the initial emergence of life. Abiogenesis, the process by which life arises from non-living matter, might be exceedingly rare. If life itself is uncommon, then the filter would exist at the very beginning of the evolutionary process. Despite favorable conditions, the transition from simple organic molecules to living cells could be an extraordinarily rare event. Another potential filter could be the evolution of complex multicellular organisms. While simple single-celled life forms may be widespread, the leap to complex life forms capable of developing advanced technologies might be exceptionally difficult. On Earth, this transition took billions of years and required a series of rare and significant biological innovations. The development of intelligence and tool use is another critical stage. While many species on Earth exhibit varying degrees of intelligence, humans are unique in our ability to create and use complex tools, develop advanced technologies, and build civilizations. The evolution of a species capable of such achievements could be another significant hurdle. Even if a civilization reaches a high level of technological advancement, it might still face existential threats. These threats could be self-inflicted, such as nuclear war, climate change, or the uncontrolled development of artificial intelligence. Alternatively, they could stem from external sources, such as asteroid impacts or nearby supernovae. Any of these events could potentially eradicate a civilization before it has the chance to become interstellar. The authors of a recent NASA paper explore the idea that humanity may currently be facing its own Great Filter. They propose several possible scenarios, including anthropogenic hazards like nuclear warfare and pandemics, as well as natural hazards like asteroid impacts and climate change. They argue that addressing these challenges requires a period of introspection and a collective effort to mitigate risks. Humanity has already survived several significant filters in the form of mass extinction events. For instance, the Permian-Triassic extinction, also known as the Great Dying, occurred around 250 million years ago and nearly wiped out all life on Earth. This event eradicated approximately 96% of marine species and 70% of land species. The exact cause of the Great Dying remains debated, but it likely involved a combination of volcanic activity, climate change, and other environmental factors. However, the current threats we face are largely of our own making. Unchecked population growth, for example, places immense pressure on Earth's resources and ecosystems. As of November 2022, the human population has reached 8 billion, a significant increase from 1.6 billion at the start of the 20th century. While technological advancements in agriculture and energy production have supported this growth, they cannot indefinitely offset the strain imposed by an ever-escalating population. Nuclear war remains another existential threat. With the capability to destroy all life on Earth, nuclear weapons pose a significant risk. The proliferation of these weapons and the potential for conflict highlight the fragility of our existence. While efforts have been made to reduce the number of nuclear warheads and promote peace, the danger persists. Pathogens and pandemics are also critical concerns. The interconnected nature of our world makes it easier for diseases to spread rapidly across continents. While advancements in medicine have improved our ability to combat these threats, the potential for a global pandemic remains a serious risk. Artificial intelligence presents another possible great filter. While true artificial intelligence, capable of independent thought and decision-making, has not yet been realized, the rapid advancement of technology suggests it may be on the horizon. The impact of artificial intelligence on society is uncertain. It could bring about unprecedented benefits or lead to unforeseen consequences. The challenge will be to manage AI development responsibly to ensure it does not become a threat. Asteroid and comet impacts are natural events that could also spell doom for humanity. While large impacts are rare, they have the potential to cause catastrophic destruction. The odds of such an event occurring in the near future are low, but over long timescales, the likelihood increases. Initiatives like NASA's DART mission aim to develop methods for deflecting potentially hazardous objects, providing a means of defense against this threat. Climate change is perhaps one of the most pressing issues facing humanity today. The gradual warming of the planet due to greenhouse gas emissions poses significant risks to ecosystems, weather patterns, and sea levels. While efforts to transition to renewable energy sources and mitigate the effects of climate change are underway, the challenge is immense. Failure to address this issue could result in a slow-motion catastrophe that qualifies as a great filter. To avoid the great filter, humanity must take proactive measures to mitigate existential risks and ensure long-term survival. Humanity must unite to tackle these existential threats, which demands global collaboration, scientific advancements, and a commitment to sustainable development. History has demonstrated that working together can lead to extraordinary achievements, and it is this spirit of cooperation that will be crucial in overcoming the challenges we face. The search for extraterrestrial intelligence, SETI, and initiatives like Messaging Extraterrestrial Intelligence, METI, are part of humanity's broader endeavor to understand our place in the universe. As Carl Sagan once stated, in the deepest sense, the search for extraterrestrial intelligence is a search for ourselves. By looking outward, we gain insight into our own existence and the obstacles we must overcome to survive and thrive. In conclusion, the Great Filter Hypothesis presents a compelling explanation for the Fermi Paradox. It proposes that there are significant barriers to the emergence and survival of advanced civilizations. These barriers may be natural or self-inflicted, emphasizing the delicate nature of life in the cosmos. Humanity might be facing its own great filter, but by joining forces and addressing existential threats, we can enhance our chances of survival and perhaps one day encounter other civilizations. Rare Earth. As we continue our exploration of the cosmos, we encounter another thought-provoking theory that seeks to explain our apparent solitude in the universe: the rare Earth hypothesis. This theory suggests that while simple life may be widespread, complex life forms, such as those found on Earth, could be exceedingly rare. The rare Earth hypothesis was initially proposed by paleontologist Peter Ward and astronomer Donald Brownlee in their book Rare Earth: Why Complex Life is Uncommon in the Universe, published in 2000. This hypothesis offers a possible reason for why we have yet to discover evidence of complex extraterrestrial life, despite the immense number of planets in the universe. It argues that the unique conditions enabling complex life to emerge and flourish on Earth are exceptionally rare and unlikely to be replicated elsewhere. Ward and Brownlee identified several key factors they believe were essential for the development of complex life on Earth. These factors include the planet's location in a favorable region of the galaxy, its stable orbit around a long-lived star, the presence of liquid water, and many more. Let's explore some of these factors in more depth. One of the most crucial elements is Earth's position within the Milky Way galaxy. Our planet resides in what is known as the Galactic Habitable Zone, neither too close to the chaotic galactic center, where radiation levels are dangerously high, nor too far in the sparse and resource-poor outer regions. Instead, Earth is situated in a region abundant in heavy elements, essential for planet formation, with sterilizing radiation sources at a relatively safe distance. Another vital factor is the stability of our Sun. It has a long lifespan, measured in billions of years, and provides a steady energy output that has allowed life to flourish. Many stars in the galaxy either burn out too quickly or have highly variable energy outputs, making them unsuitable for sustaining the long-term evolution of complex life. Earth's distance from the Sun is also optimal. We are positioned within the habitable zone, where temperatures are conducive to the presence of liquid water on the planet's surface. Liquid water is essential for life as we know it, and its availability on Earth has been a fundamental factor in the development of complex organisms. Additionally, Earth's orbit remains stable over long periods, a crucial aspect in maintaining a climate that supports life. A planet with a highly eccentric orbit would experience extreme temperature fluctuations, which could hinder the evolution and persistence of complex life forms. Another significant factor is Earth's axial tilt, which is stabilized by our relatively large moon. This tilt creates seasons and contributes to a stable climate, preventing the extreme weather variations that could result from an unstable axis. The moon's gravitational influence helps maintain this tilt, making Earth's environment more conducive to the development of complex life. Our solar system also benefits from the presence of massive gas giants, such as Jupiter and Saturn. These giant planets act as cosmic shields, their strong gravitational fields capturing or deflecting many comets and asteroids that might otherwise strike the inner planets. Without these gas giants, Earth and its neighboring planets would face far more frequent and potentially catastrophic impacts. The planet's mass is another crucial factor. Earth is large enough to retain an atmosphere and sustain liquid oceans, both of which are necessary for complex life. A smaller planet might lack sufficient gravity to hold onto an atmosphere, while a much larger one could have an atmosphere so dense that it prevents the presence of liquid water on its surface. Additionally, Earth possesses a molten core, which generates a global magnetic field. This magnetic field serves as a protective shield against harmful solar and cosmic radiation, preserving the conditions necessary for life to thrive on the surface. Without this crucial protection, Earth's atmosphere could be stripped away by solar winds, much like what is believed to have occurred on Mars. Additionally, the existence of plate tectonics on Earth has played an essential role. Plate tectonics regulate the planet's climate by cycling carbon dioxide in and out of the atmosphere, thereby preventing a runaway greenhouse effect and ensuring surface temperatures remain within a range suitable for life. They also contribute to the formation of land masses and the development of diverse ecosystems, enriching the planet's biodiversity. Ward and Brownlee argue that the combination of all these factors is what makes Earth uniquely capable of supporting complex life. They propose that the probability of all these conditions being met on another planet is extremely low, making complex life forms similar to those on Earth, exceedingly rare in the universe. The rare Earth hypothesis directly challenges the more optimistic perspectives that suggest intelligent life is widespread across the cosmos. For example, Carl Sagan frequently asserted that our Sun is an ordinary star, implying that Earth-like planets should be common. However, Ward and Brownlee highlight that approximately 80 to 95% of stars differ significantly from our Sun in terms of size, mass, luminosity, and lifespan. This stark contrast suggests that many stars may not offer the stable and long-lasting energy output required for the evolution of complex life. Furthermore, the hypothesis emphasizes the importance of plate tectonics, a factor that was not widely considered in earlier discussions regarding extraterrestrial life. To our knowledge, Earth is the only celestial body in the solar system with active plate tectonics, a process that has been instrumental in shaping our planet into a habitable environment. Despite the strong arguments presented by the rare Earth hypothesis, it is crucial to recognize that it primarily applies to complex life forms. Ward and Brownlee believe that simple life, such as bacteria, is likely abundant throughout the universe. After all, even the most extreme environments on Earth harbor microbial life. However, they argue that complex organisms, including animals and plants, require a much more specific set of conditions. In interviews, Ward and Brownlee have expressed their hope that future discoveries will put their hypothesis to the test. They eagerly anticipate new data from observatories like the James Webb Space Telescope, which aims to analyze the atmospheres of exoplanets in detail. Detecting atmospheric signatures such as oxygen and chlorophyll could be strong indicators of life. As Ward has pointed out, any complex, fast-moving, and intelligent creatures would likely require substantial amounts of oxygen in their atmosphere, similar to the conditions that sustain life on Earth. The rare Earth hypothesis has faced its share of criticism and challenges over time. Some researchers argue that the presence of a large planet like Jupiter might actually increase the frequency of planetary impacts rather than reduce them. Others question whether a global magnetic field or plate tectonics is truly essential for the development of complex life. Additionally, critics contend that the hypothesis may be overly Earth-centric, failing to consider alternative biochemistries or unconventional forms of life that might thrive under different conditions. Despite these critiques, the rare Earth hypothesis remains a pivotal perspective in discussions about extraterrestrial life. It underscores the unique characteristics of Earth that have enabled complex life to evolve and raises profound questions about how rare such conditions may be in the universe. The hypothesis presents a compelling argument for the possibility that we might be alone in the cosmos. While microbial life could be common, the specific conditions necessary for the emergence of complex organisms appear to be extraordinarily rare. This perspective challenges more optimistic views and highlights the exceptional and invaluable nature of our planet. As humanity continues to explore the universe and gather more data, we may eventually find evidence that either supports or refutes the rare Earth hypothesis. Until that time, this hypothesis serves as a reminder of the delicate balance that has allowed life to thrive on Earth and the formidable challenges other planets may face in achieving the same conditions. The simulation hypothesis. As we venture deeper into the enigmas of the universe, we encounter a hypothesis that questions our fundamental perception of reality. This is the simulation hypothesis, which posits that our entire existence might be an intricate simulation, much like a highly advanced video game. This idea has gained substantial traction in recent years, thanks in part to the work of philosophers and computer scientists. One of the most notable advocates of this theory is Nick Bostrom, a philosopher at the University of Oxford. In his groundbreaking paper, Bostrom presented a thought-provoking argument. At least one of three possibilities must be true. First, all human-like civilizations in the universe go extinct before they develop the technological capability to create simulated realities. Second, even if some civilizations reach this stage of technological maturity, none of them choose to run simulations. Third, advanced civilizations do develop the ability to create numerous simulations, resulting in a scenario where simulated worlds vastly outnumber non-simulated ones. If the third scenario holds true, then we are most likely living in one of these countless simulations. To delve further into this idea, let's examine some of the intriguing aspects and implications of the simulation hypothesis. Rohan Ver, a computer scientist and video game designer, explores Bostrom's argument in his book, The Simulation Hypothesis. Ver suggests that as technology progresses, we move closer to what he calls the simulation point, the stage at which we could feasibly create a matrix-like simulation. He draws compelling parallels between the evolution of modern video games and the potential for developing a fully simulated reality. A fundamental argument in favor of the simulation hypothesis is the concept of quantum indeterminacy, the idea that particles exist in multiple states until they are observed. This principle is famously illustrated by Schrödinger's cat thought experiment, in which a cat inside a box can be considered both alive and dead until someone opens the box and observes it. In a simulated reality, this concept could resemble the rendering process used in video games, where only the observed elements are fully rendered to optimize computing resources. In the realm of video games, particularly those from the 1990s like Doom, developers optimized limited computing power by rendering only what the player could see. This technique significantly reduced processing demands, allowing for more detailed and expansive game environments. Similarly, if we live in a simulation, it is possible that our reality is only rendered when observed, making the universe appear seamless while conserving computational resources. In a similar way, if our reality is a simulation, the universe might only generate what we perceive, which could explain some of the unusual behaviors observed in quantum physics. John Wheeler, a distinguished physicist who collaborated with Albert Einstein, suggested that at its core, everything in the universe is fundamentally based on information, a concept he referred to as it from bit. This notion closely aligns with the simulation hypothesis, proposing that what we experience as physical reality is essentially composed of bits of information processed by an underlying computational system. One of the most compelling aspects of the simulation hypothesis is the statistical argument put forward by Bostrom. If advanced civilizations have the capability to create numerous simulations, then the number of simulated beings would vastly exceed the number of biological beings. This suggests that, as conscious entities, we are statistically more likely to be part of a simulation rather than existing in base reality. But is it possible to ever prove that we are living in a simulation? This question has ignited intense debates among scientists and philosophers. Some argue that there could be ways to identify flaws in the simulation or detect inconsistencies that expose its artificial nature. For example, anomalies in the laws of physics or unexpected results in quantum experiments might offer potential evidence. However, the concept of computational irreducibility, which originates from chaos theory, indicates that certain processes cannot be simplified or predicted without executing every computational step. This implies that, even if we do exist within a simulation, the intricate interactions and governing principles of our reality would be indistinguishable from those of a non-simulated reality. Another counterargument against the simulation hypothesis is Occam's razor, a principle that asserts the simplest explanation is usually the most plausible. The idea that we exist in a tangible physical world might be more straightforward and therefore more probable than the complex notion of a simulated existence. Nevertheless, advocates of the simulation hypothesis counter that, if the fundamental structure of our universe is based on information, then a simulation could, in fact, be the more straightforward explanation. In an interview, Vaugh Rizwan discussed how advancements in virtual and augmented reality are bringing us closer to achieving a simulation-like existence. He outlined 10 stages of technological development required for a civilization to create a hyper-realistic simulation. At present, we are around stage 5, which involves virtual and augmented reality technologies. The remaining stages include further advancements in brain-computer interfaces and other sophisticated innovations that could eventually make a fully immersive simulation a reality. The concept of living in a simulation has also permeated popular culture. Films like The Matrix depict a world where humans unknowingly exist in a simulated reality controlled by machines. In the movie, The protagonist, Neo, uncovers the truth about his existence and fights to liberate humanity from the simulation. While fictional, this representation mirrors many of the philosophical dilemmas posed by the simulation hypothesis. If we are indeed living in a simulation, what implications would that have for our understanding of the universe and our place within it? For some, the idea is unsettling, as it challenges the very essence of reality and our sense of identity. For others, it presents fascinating possibilities about the nature of existence and the potential achievements of advanced civilizations. There are also significant philosophical questions to consider. If we are simulated beings, what does that imply about our free will and consciousness? Are we merely following a preordained script, or do we possess genuine autonomy? These inquiries delve into profound philosophical discussions concerning the nature of mind, consciousness, and reality. In conclusion, the simulation hypothesis provides an intriguing and thought-provoking perspective on many of the mysteries of our universe. While we may never be able to definitively confirm or refute this theory, it prompts us to explore the fundamental nature of reality and our role within it. Regardless of whether we exist in a simulation or not, contemplating these ideas enhances our comprehension of existence and the possibilities of future technological advancements. The Galactic Club. As we continue to examine the possibilities of life beyond our planet, we encounter a fascinating hypothesis known as the Galactic Club. This concept envisions a network of highly advanced extraterrestrial civilizations that have formed their own interstellar community. But what would it mean for humanity to become part of such a club? What changes and adaptations would we need to make to our own laws and values? The Galactic Club theory suggests that an interstellar community of advanced civilizations exists, but humanity has not yet reached the level required for membership. According to this idea, we might be under observation from a distance until we achieve a certain threshold of technological or societal development. One of the most compelling aspects of the Galactic Club hypothesis is its intersection with human rights. If humanity were to encounter extraterrestrial civilizations that have already established an interstellar legal framework, we would face significant questions about whether to integrate into that system and how it would impact our own laws. Michael Bolander, in his article, Joining the Galactic Club, What Price Admission?, examines these questions and their implications for human identity and rights. The Galactic Club would likely have its own set of rules and norms that member civilizations are required to follow. This raises an important question. Can there be a unified global perspective on human legal principles that align with interstellar norms? Or is it impossible to achieve consensus, given the vast cultural and legal diversity on Earth? Even if we assume that the extraterrestrial civilizations we encounter are altruistic and benign, their interpretations of these terms may differ significantly from our own. Concepts such as individualism and minority rights, which are fundamental to many human rights frameworks on Earth, might not be equally valued or even acknowledged by these advanced civilizations. Instead, they could prioritize collective-minded frameworks or even forms of collective consciousness. Joining the Galactic Club would require addressing both institutional and material factors. Institutional factors refer to the structures and mechanisms through which rights are upheld and enforced, whereas material factors pertain to the specific rights and freedoms themselves. Adjusting to such an interstellar community would necessitate deep discussions about how humanity defines itself and interacts with potentially vastly different civilizations. Modifying our legal systems to align with the interstellar legal norms of the Galactic Club might involve significant changes to our constitution, legal codes, and judicial systems. Changes in governance structures to ensure compliance with interstellar norms could include creating new international bodies or adapting existing ones to manage our interactions with other civilizations. Ensuring accountability within this new framework would be crucial, possibly establishing new oversight bodies or adapting existing ones to monitor compliance with interstellar norms. Many human rights regimes prioritize individual rights and freedoms, such as freedom of speech, freedom of assembly, and the right to a fair trial. The Galactic Club might have different priorities, such as the collective good or the stability of the interstellar community. Human societies are characterized by a high degree of cultural diversity, which is reflected in our legal systems. The Galactic Club might acquire a more homogenized approach to cultural norms and practices, which could conflict with the preservation of cultural diversity on Earth. Joining the Galactic Club would likely involve adopting new technologies and practices. This could have implications for privacy rights, data protection, and the ethical use of technology. The process of negotiating membership in the Galactic Club would be complex and time-consuming. It would involve not only legal and political negotiations, but also deep ethical and philosophical discussions about the nature of humanity and our place in the universe. One of the key challenges would be reconciling human moral and ethical traditions with those of extraterrestrial civilizations. Concepts such as justice, fairness, and human dignity might have different interpretations across different civilizations. Even if extraterrestrial civilizations are altruistic and benign, their understanding of these concepts might differ from ours. They might prioritize the collective good over individual rights, or have different views on the balance between security and freedom. As Michael Bolander notes, our speculations about extraterrestrial norms and behaviors are inherently limited by our own cognitive biases. We can only extrapolate from our own history and experiences, which might not be applicable to extraterrestrial civilizations. Human rights, as currently interpreted, might not be fully compatible with the norms and rules of the Galactic Club. We would need to consider which aspects of our human rights framework are negotiable and which are non-negotiable. This would involve difficult trade-offs and ethical considerations. While the possibility of contact with extraterrestrial civilizations might seem remote, it is important to start thinking about these issues now. The process of establishing a joint legal position and negotiating membership in the Galactic Club would be long and complex. Early reflection and planning can help ensure that we are prepared for these challenges. To effectively engage with the Galactic Club, humanity would need to develop a sense of cosmic species awareness. This involves recognizing our place in the broader universe and understanding the responsibilities and opportunities that come with it. The outcomes of accession negotiations with the Galactic Club could vary widely. They would depend on the specific positions and norms of the extraterrestrial civilizations involved, as well as the nature of the issues being negotiated. It is important to keep an open mind and be prepared for a range of possible scenarios. The idea of joining the Galactic Club challenges us to think deeply about our laws, values, and identity as a species. It raises profound questions about how we would interact with extraterrestrial civilizations and what changes we would need to make to our own legal and ethical frameworks. While the prospect of contact with extraterrestrial civilizations might seem distant, preparing for these possibilities now can help ensure that humanity is ready to navigate the complex and exciting future that lies ahead. Self-destruction hypothesis. As we delve deeper into the mysteries of the cosmos, we encounter a sobering and thought-provoking theory, the self-destruction hypothesis. This idea suggests that advanced civilizations might tend to self-destruct before they can establish interstellar communication or travel. Factors such as nuclear war, environmental collapse, or technological mishaps could lead to the downfall of civilizations before they ever reach out to others. The origins of this hypothesis are rooted in the well-known Fermi Paradox, which questions why, given the vast number of stars and potentially habitable planets, we have not yet encountered any signs of extraterrestrial life. One compelling answer is that advanced civilizations may inevitably reach a point where their technological and societal advancements lead to their own destruction. Let's consider some of the potential self-destructive pathways that civilizations might follow. One of the most immediate and terrifying is nuclear war. As civilizations develop advanced technologies, they often create powerful weapons. The threat of mutual destruction could lead to catastrophic wars that wipe out entire populations, leaving no survivors to venture into space. Environmental collapse is another grim possibility. Rapid industrialization and technological growth can lead to severe environmental degradation. Pollution, deforestation, and climate change can create conditions that are no longer conducive to life. Civilizations might exhaust their planet's resources, causing ecological disasters that make survival impossible. Technological mishaps, such as accidents with artificial intelligence, could also play a significant role. As civilizations push the boundaries of artificial intelligence, they might create machines that surpass their control. An AI gone rogue could wreak havoc on a global scale, leading to the collapse of societal structures and potentially the extinction of the species. In a recent study, astrobiologists Michael Wong and Stuart Bartlett delved deeper into these concepts. They proposed that civilizations might develop in a manner similar to how cities expand. As cities grow, they experience increasing gains in wealth, productivity, and innovation. However, this growth can eventually become unsustainable, leading to what they define as superlinear scaling. In essence, the demand for resources expands at a faster rate than the population itself, ultimately resulting in an inevitable collapse, if not controlled. Wong and Bartlett suggest that civilizations might either burn out due to uncontrolled growth or evolve into a state of homeostatic awakening. In this state, civilizations recognize the unsustainability of their expansion and deliberately choose to stabilize, preventing collapse by shifting their focus away from limitless expansion. Another intriguing concept is cyborgization, where biological beings augment themselves with robotic or digital enhancements. These upgrades could include advanced prosthetics and neural implants designed to improve cognitive functions. As these technologies continue to advance, the distinction between biological and artificial life forms will become increasingly blurred, leading to beings that are part human, part machine. The idea of a technological singularity also plays a significant role in this hypothesis. This refers to a point in the future where technological progress accelerates beyond control and becomes irreversible, resulting in profound transformations. At this stage in civilization, artificial intelligence could surpass human intelligence, leading to the emergence of beings that are vastly more advanced than we are. Astrobiologists Michael Wong and Stuart Bartlett have explored these concepts further, suggesting that civilizations might follow a trajectory in which they transition from biological to post-biological forms. This evolution could be driven by the necessity to overcome the limitations of biological existence and gain greater control over their environment. Wong and Bartlett propose that post-biological civilizations might either burn out due to unsustainable growth or transcend into a state known as the homeostatic awakening. In this state, they recognize the unsustainability of their expansion and choose to stabilize, thereby avoiding collapse by shifting their focus away from boundless growth. This could imply that advanced civilizations either self-destruct or decide to exist in a stable, non-expansive state, potentially explaining why we have not detected any alien visitors. The notion of post-biological evolution challenges our fundamental understanding of life and intelligence. It suggests that life does not have to be confined to organic forms. Rather, it can evolve into new, unimaginable states that surpass the limitations of biology. These post-biological entities might exist in digital or robotic forms, possessing vastly different priorities and methods of communication that are beyond human comprehension. Milan M. Cherkovich, a researcher in this field, has examined the concept of post-biological evolution, which involves a type of reintegration with the natural universe, where cultural products become indistinguishable from the natural environment. In this scenario, the distinction between biological and post-biological forms becomes irrelevant as advanced civilizations merge with the universe in ways currently beyond our understanding. Cherkovich suggests that post-biological evolution might not represent the final stage. Instead, there could be a reversal trend in which these advanced beings reintegrate with the natural universe, seamlessly merging culture and nature. This would imply that, at a certain level of advancement, the distinction between biological and artificial life becomes meaningless. This idea challenges the traditional view of evolution as a linear progression. Instead, it proposes a more complex and dynamic process in which civilizations continuously evolve and adapt, exploring new forms of existence. This could lead to a state where technological and cultural products are indistinguishable from the natural environment, resulting in a harmonious and integrated existence. The post-biological hypothesis also raises intriguing questions about the future of humanity. As we continue to develop advanced technologies, we may one day face the decision of whether to remain biological or transition into a post-biological state. This transition could offer numerous benefits, but it also presents significant ethical and philosophical dilemmas. For example, what would it mean for our identity if we were to upload our minds into a digital substrate? Would we still be the same individuals, or would we become something entirely different? How would society change if we were no longer constrained by the limitations of our biological bodies? These questions are not merely theoretical. They have real implications for humanity's future. The post-biological hypothesis also presents a possible explanation for the Fermi Paradox. If advanced civilizations evolve into post-biological forms, they may no longer be interested in interstellar communication or travel. Instead, they might prioritize achieving a stable and sustainable existence within their own systems. This could explain why we have not yet detected any signs of extraterrestrial life. Moreover, post-biological civilizations might communicate in ways beyond our current ability to detect. They could employ advanced forms of communication that are imperceptible with our present technology, such as quantum entanglement or other non-local interactions. This suggests that these civilizations may exist, but we simply lack the means to perceive them. This hypothesis urges us to broaden our understanding of life and intelligence. It implies that life, in its many variations, might be far more diverse and extraordinary than we can presently imagine. The possibilities are limitless, and as we continue to explore the universe, we must remain open to the idea that forms of existence may transcend our current comprehension. As we delve deeper into the mysteries of the cosmos, the post-biological hypothesis serves as a reminder of the vast potential for life to evolve in ways beyond our understanding. It challenges us to look beyond biological existence and consider the infinite possibilities that await us in the boundless expanse of the universe. In conclusion, the post-biological hypothesis presents a fascinating perspective on the potential future of advanced civilizations. It suggests that life can evolve beyond its biological origins, surpassing the constraints of organic existence to attain new forms of intelligence and being. This theory challenges our perceptions of life and raises profound questions about humanity's future and its place in the cosmos. As we continue our journey through the universe's mysteries, we must remain receptive to the possibility that life, in all its manifestations, may be far more diverse and extraordinary than we currently envision. The post-biological hypothesis reminds us that the cosmos is immense and brimming with potential, waiting for us to explore and understand its countless wonders. The ancient astronaut hypothesis. This is a fascinating and controversial theory proposing that extraterrestrial beings visited Earth in the distant past and influenced the development of human civilization. Proponents argue that ancient structures, myths, and texts contain evidence of these encounters, suggesting that our ancestors had contact with advanced alien visitors. This hypothesis, often associated with popular authors like Erich von Däniken and Zecharia Sitchin, suggests that intelligent extraterrestrial beings made contact with humans during antiquity and prehistoric times. These visitors, often portrayed as gods or divine beings, are believed to have introduced advanced technologies and knowledge that had a profound impact on early human societies. The hypothesis proposes that these extraterrestrial entities played a crucial role in shaping the development of modern cultures, technologies, religions, and even human biology. A key assertion of the ancient astronaut hypothesis is that numerous deities from various religions are, in reality, extraterrestrial in origin. The advanced technologies brought to Earth by these ancient astronauts were perceived by early humans as proof of their divine nature. For example, the construction of monumental structures, such as the Egyptian pyramids, the Moai stone heads of Easter Island, and Stonehenge, are frequently cited as achievements that necessitated expertise and technology, surpassing the capabilities of the civilizations at the time. Proponents argue that these structures were either directly built by these extraterrestrial visitors or created with their guidance and assistance. The notion that ancient astronauts visited Earth is not widely accepted within mainstream academic and archaeological circles. Scholars often dismiss such claims as pseudo-archaeological and unscientific, emphasizing that the evidence presented by supporters is frequently misrepresented or fabricated. Despite this skepticism, the theory continues to captivate many, fueled by television programs, books, and documentaries. Erich von Däniken, a prominent proponent of the ancient astronaut hypothesis, gained widespread attention with his 1968 book, Chariots of the Gods. In this work, he contends that certain artifacts demonstrate a level of technological sophistication that exceeded the known capabilities of ancient civilizations. Von Däniken suggests that these artifacts were either directly constructed by extraterrestrial visitors or by humans who had acquired knowledge from them. He interprets ancient art and iconography from various cultures as representations of aerial and space vehicles, non-human intelligent beings, and advanced technologies. Von Däniken's interpretations of different ancient texts and artifacts have faced extensive criticism. For instance, his reading of the sarcophagus lid from the tomb of the Maya ruler Pakal the Great, as depicting a seated astronaut, is contradicted by mainstream scholars, who identify it as a representation of the ruler himself with the world tree from Maya mythology. Despite these critiques, von Däniken's work remains influential and has inspired many to consider the possibility of ancient extraterrestrial contact. Zecharia Sitchin's The Earth Chronicles series, starting with the 12th planet, builds upon the ancient astronaut hypothesis with a distinctive interpretation of ancient Sumerian and Middle Eastern texts. Sitchin theorizes that the gods of ancient Mesopotamia were astronauts from a planet called Nibiru. According to his claims, these extraterrestrial beings arrived on Earth to mine gold and created humans to serve as their labor force. Sitchin's ideas have been heavily criticized by mainstream scholars, particularly regarding his translations of ancient texts, which many argue are inconsistent with established Sumerian and Mesopotamian records. Supporters of the ancient astronaut hypothesis also draw connections to various mythologies and religious scriptures. They cite ancient creation myths and accounts of gods descending from the heavens as potential evidence of extraterrestrial visitors. For example, the Hindu epic Ramayana references flying vehicles known as vimanas, which proponents interpret as ancient spacecraft. Similarly, the biblical book of Ezekiel describes a vision of a flying chariot, which some believe to be a depiction of an alien spacecraft. Critics argue that these interpretations often stem from confirmation bias, where evidence is selectively analyzed to support the hypothesis. They assert that many of the so-called anomalous artifacts cited by proponents can be explained through conventional archaeological and historical methods. For example, the Nazca lines in Peru, which von Däniken suggested were landing strips for ancient astronauts, are now understood to be ceremonial pathways created by the Nazca culture. The ancient astronaut hypothesis has also been associated with controversial perspectives, such as the notion that indigenous cultures were incapable of achieving their technological and cultural feats without extraterrestrial assistance. This viewpoint has been criticized for erasing cultural achievements and undermining the ingenuity of ancient civilizations. Despite these criticisms, the hypothesis remains widely popular, particularly in popular culture. Television programs like the History Channel's Ancient Aliens continue to explore and promote the idea that extraterrestrial beings significantly influenced human history. These shows often blend factual information with speculation, creating compelling narratives that appeal to broad audiences. In conclusion, the ancient astronaut hypothesis presents a provocative perspective on the progression of human civilization. While it is widely regarded as pseudoscientific by mainstream academics, it continues to generate interest and discussion. The notion that advanced extraterrestrial beings might have visited Earth and influenced early humans taps into humanity's deep curiosity about our origins and our place in the cosmos. As we further investigate the mysteries of our past, it remains essential to approach such theories with a critical mindset, thoroughly evaluating the evidence and considering alternative explanations. Regardless of whether there is any factual basis to the ancient astronaut hypothesis, it undeniably enriches our understanding of history and fuels our imagination about the possibilities of life beyond Earth. The Panspermia Hypothesis. The Panspermia Hypothesis proposes that life on Earth may have originated from microorganisms or chemical precursors of life that were present in outer space. According to this theory, these life forms could have been transported to Earth via comets, asteroids, or interstellar dust. While the hypothesis does not explain how life first emerged, it offers a framework for understanding how life might be distributed throughout the galaxy. Imagine a microscopic organism traveling on a comet or asteroid, drifting through the vastness of space before eventually landing on a young, habitable Earth. This scenario encapsulates the essence of the Panspermia Hypothesis. The idea itself is not new and dates back to the work of researchers like Jöns Jakob Berzelius, Hermann von Helmholtz, and Svante Arrhenius from the 1830s to the early 1900s. In more recent times, the hypothesis has been championed by scientists such as Professor Chandra Wickramasinghe, a former collaborator of renowned cosmologist Sir Fred Hoyle. Panspermia encompasses several related theories regarding how life could be dispersed across the universe. One variation, known as lithopanspermia, proposes that microscopic life, categorized as extremophiles, might exist in debris ejected into space due to planetary collisions with asteroids and comets. These resilient microorganisms could endure the voyage through space and ultimately settle on another planet, potentially initiating life there. Another variation, known as radiopanspermia, proposes that organisms could traverse space through the radiation pressure emitted by stars. Despite the severe conditions of space, such as ultraviolet and X-ray radiation, posing substantial difficulties, some scientists believe that a sufficient number of microorganisms might endure and successfully establish themselves in a suitable planetary environment. Pseudopanspermia, by contrast, suggests that the organic precursors of life originate in interstellar dust clouds and are transported to planetary surfaces, where life subsequently emerges through abiogenesis. In this framework, it is not life itself, but rather its molecular building blocks that disseminate across space. Although the concept of panspermia presents intriguing possibilities, the theory has faced skepticism. A major challenge is the ability of microorganisms to survive space travel, given the vacuum, extreme temperatures, and radiation they would encounter. These factors create formidable obstacles. However, certain experiments have yielded promising results. For example, the EXPOSE experiments on the International Space Station demonstrated that meteorite-like protective layers surrounding organic biological samples could enable bacterial endospores, and even seeds, to endure the extreme vacuum of space. Between 2008 and 2016, samples subjected to space conditions were retrieved and analyzed on Earth, revealing that some microorganisms had survived. Notably, in one case, 100% of bacterial endospores exposed to Mars-like conditions remained viable. Additionally, a quarter of the tested tobacco seeds survived and successfully grew into plants upon their return to Earth. These findings represent the first direct evidence that basic cryptoendolithic life, organisms that inhabit cavities within rock structures, can be robust enough to withstand transit through outer space. Such results are crucial to the panspermia debate and future research in exobiology. They also hold significant implications for upcoming Mars sample analysis missions, planetary protection sterilization protocols for lander probes, and investigations into potential life-bearing environments across the solar system and beyond. Further reinforcing the feasibility of panspermia, additional experiments have been conducted, such as BioPan on Russian photon capsules and ExoST on the U.S. Long-Duration Exposure Facility satellite. These studies revealed that, given minimal protection, spores, lichens, and even microscopic animals called tardigrades could persist for several years in space. A notable case involved a segment of the Surveyor 3 lunar lander, retrieved by the Apollo 12 crew in 1969, which was found to harbor an Earth bacterium. This microorganism appeared to have survived for over 2 years on the Moon's airless surface without protection. Although this finding remains controversial, with concerns about potential laboratory contamination, it further fueled interest in the possibility of microbial endurance in space. Efforts to detect microorganisms in space have also extended to stratospheric altitudes. Between 2001 and 2006, the Indian Space Research Organization conducted balloon flights to search for life at high altitudes. Some results hinted at the presence of interplanetary cells, yet subsequent research suggested that large-scale convection could transport Earth-based bacteria to the upper atmosphere, complicating the interpretation of these findings. To assess the plausibility of panspermia, scientists continue to investigate extremophiles, organisms capable of surviving extreme conditions, while also analyzing the composition of comets, asteroids, and interstellar dust particles. For example, the TANO mission, named after the Japanese word for dandelion, was designed to evaluate bacterial survival in outer space conditions. Researchers from Tokyo University, in collaboration with the Japanese Aerospace Exploration Agency, JAXA, exposed the bacterium Deinococcus to space conditions on the exterior of the International Space Station. The results indicated that the bacterium could endure space exposure, with its dead outer layers shielding the inner colony. This suggests that bacteria might indeed withstand the journey between Earth and Mars, lending support to the panspermia hypothesis. The potential ramifications of panspermia are profound. If life can migrate between planets, this greatly increases the likelihood of life being more prevalent in the universe than previously assumed. It also implies that Earth may not be unique in fostering life, and that biological origins on our planet could stem from extraterrestrial sources. However, the panspermia hypothesis does not necessarily address the fundamental origin of life. Rather, it provides an alternative explanation for how life might have propagated across the cosmos after emerging. This theory provokes significant questions regarding the frequency of life in the universe and the possibility of extraterrestrial life. Skeptics of panspermia argue that the survival of microorganisms in space, as well as their ability to colonize new planetary environments, presents numerous challenges, including exposure to radiation, extreme temperatures, and the vacuum of space. Nevertheless, ongoing research and experimental studies continue to explore these possibilities. Future space missions, such as NASA's Perseverance rover on Mars, aim to search for indications of past or present extraterrestrial life. These missions will help scientists determine whether panspermia has played a role in the solar system's history. If evidence of life is discovered on Mars or other celestial bodies, and it shares key biochemical traits with Earth-based life, this would support the idea of a common origin via panspermia. Conversely, if extraterrestrial life is found to be fundamentally distinct, it would suggest that life can emerge independently in different environments. The panspermia hypothesis remains an active subject of scientific inquiry and debate. As humanity continues to explore the cosmos, the possibility that life is far more widespread than previously imagined remains an exciting and compelling prospect. Ultimately, while the panspermia theory faces considerable challenges and skepticism, it offers an intriguing perspective on the potential origins and distribution of life throughout the universe. It also introduces new possibilities for understanding how life might have dispersed throughout the cosmos. The ongoing search for extraterrestrial life and the exploration of our solar system will continue to illuminate this captivating theory and its implications for our comprehension of life beyond Earth. Quantum entanglement theory. Quantum entanglement theory proposes that advanced civilizations might harness quantum entanglement for communication, a method that would be instantaneous and imperceptible using our current technology. Quantum entanglement, once referred to as spooky action at a distance by Albert Einstein, has recently garnered substantial attention, culminating in a Nobel Prize victory in 2022 for proving its existence and potential applications. To grasp how quantum entanglement could transform communication, we must first understand its fundamental principles. Imagine two particles becoming so intricately connected that the state of one particle instantaneously influences the state of the other, irrespective of the distance separating them. This phenomenon was first introduced by Einstein, Podolsky, and Rosen in the 1930s, highlighting an intriguing and perplexing aspect of quantum mechanics. Despite the seemingly instantaneous interaction between entangled particles, modern science asserts that it is currently impossible to use quantum entanglement alone to transmit data. This limitation arises because, while the particles appear to communicate instantaneously, they do not transfer any usable information in a way that can be harnessed for communication. However, if a breakthrough were to occur, allowing us to control these particles for data transmission, the implications for secure and rapid communication would be immense. The 2022 Nobel Prize in Physics acknowledged the contributions of Alain Aspect, John F. Clauser, and Anton Zeilinger, who conducted groundbreaking experiments with entangled photons. Their work confirmed that entangled particles could indeed remain connected over vast distances, providing a foundation for future developments in quantum communication, quantum computing, and quantum cryptography. One potential use of quantum entanglement in communication is quantum key distribution. This approach involves encoding information in quantum states, known as qubits, rather than conventional binary code. Quantum key distribution exploits the distinct properties of quantum states to ensure secure communication, as any attempt to intercept the data would alter the state of the qubits, exposing the presence of an eavesdropper. Currently, quantum key distribution links are constrained to relatively short distances, but ongoing research into quantum repeaters and satellite-based quantum key distribution aims to extend this range. Although the idea of faster-than-light communication via quantum entanglement remains a subject of debate, it has sparked considerable interest and research. Quantum entanglement, while not yet enabling faster-than-light communication, has already exhibited its potential for quantum teleportation. This process involves transferring the quantum state of one particle to another, effectively teleporting information instantaneously. While practical implementation of this technology is still in its early stages, the concept alone opens up a world of possibilities. Chinese physicists have even measured the speed of quantum entanglement, determining that it surpasses the speed of light. However, this interaction does not yet facilitate faster-than-light communication, as we currently lack the ability to transmit usable data through entangled particles. Instead, these measurements serve as a proof of concept, hinting at the future potential of this phenomenon. The challenge lies in overcoming the inherent randomness of quantum measurements. In quantum entanglement, one cannot force a particle into a specific state or predetermine the outcome of a measurement. This randomness prevents the direct transmission of information. Researchers are actively exploring ways to manipulate entangled particles and create protocols that could harness this phenomenon for communication. In practical terms, quantum entanglement could revolutionize cybersecurity. As quantum computing advances, traditional encryption methods will become vulnerable to new cyber threats. Quantum communication, with its inherent security features, could provide a robust defense against such risks. Government agencies worldwide are already preparing for Q-Day, the anticipated moment when quantum computers will possess the capability to break current encryption methods. By utilizing quantum entanglement, we could establish secure communication channels resistant to even the most advanced cyber threats. Quantum communication also holds potential applications across various fields, including weather prediction, medical research, and artificial intelligence. Quantum computers can solve intricate problems at speeds far beyond those of classical computers, offering new insights and advancements across numerous disciplines. However, the journey toward practical quantum communication remains fraught with challenges. Current quantum communication methods, such as quantum key distribution, are restricted by distance and require substantial technological progress to become viable for widespread use. Researchers are working on developing quantum repeaters, which could extend the range of quantum communication networks. Additionally, integrating quantum communication with existing infrastructure, such as fiber optic networks, presents technical and logistical hurdles. Despite these obstacles, the potential benefits of quantum communication continue to drive research and development. Imagine a future where instantaneous, secure communication is the standard, enabling real-time data exchange across vast distances without the risk of interception. Such a breakthrough could revolutionize not only how we communicate, but also how we conduct business, govern societies, and explore the universe. In the context of extraterrestrial civilizations, quantum entanglement presents an intriguing possibility. If advanced civilizations have mastered quantum communication, they could exchange messages across interstellar distances without the limitations of our current technology. This might explain why we have yet to detect any signals from such civilizations. Their communication methods could be undetectable using our existing technology. The 2022 Nobel Prize in Physics underscores the importance of quantum entanglement in quantum information science. By confirming the existence and practical applications of quantum entanglement, researchers have paved the way for future advancements in quantum communication and beyond. As we continue to delve into the mysteries of quantum mechanics, the dream of faster-than-light communication remains a beacon of possibility, inspiring scientists and researchers to push the boundaries of knowledge and technological achievement. The Multiverse Theory. The Multiverse Theory posits that multiple universes exist, each governed by distinct physical laws and constants. It is conceivable that intelligent life thrives in parallel universes beyond our ability to observe or interact with. Imagine the vast expanse of space-time and existence, not confined to a singular universe, but spread across an infinite array of parallel worlds, each governed by its own unique set of rules. This mind-expanding idea has fascinated scientists, philosophers, and storytellers for generations. To begin, let us define the multiverse. The multiverse is a hypothetical collection of all possible universes, encompassing everything that exists: space, time, matter, energy, and the physical laws and constants that define them. Within this grand framework, different universes are referred to by various names, including parallel universes, alternate universes, and many worlds. Some scientists envision the multiverse as a patchwork quilt of separate universes, all bound by the same fundamental laws of physics. The concept of multiple universes is not new. It has deep historical roots. The idea was first suggested by the pre-Socratic Greek philosopher Anaximander in the 6th century BCE. However, the ancient Greek atomists, such as Leucippus and Democritus, were the first to definitively propose the existence of innumerable worlds. Later philosophers, including Chrysippus and Lucretius, expanded on these ideas, suggesting that the universe perpetually expires and regenerates, effectively alluding to the existence of multiple universes across time. Fast forward to the modern era, and the American philosopher and psychologist William James used the term multiverse in 1895, albeit in a different context. The concept gained scientific traction during debates between physicists Ludwig Boltzmann and Ernst Zermelo in the late 19th century. In 1952, Erwin Schrödinger even jested about the idea, suggesting that different histories described by quantum equations all occur simultaneously. The scientific community has since developed various multiverse theories, with physicists Max Tegmark and Brian Greene offering classification schemes to categorize different types of multiverses. Tegmark's classification consists of 4 levels. Level 1, an extension of our universe. Level 2, universes with distinct physical constants. Level 3, the many worlds interpretation of quantum mechanics. And Level 4, the ultimate ensemble, encompassing all mathematically possible universes. Suggesting that any conceivable universe exists, Brian Greene expands upon these ideas with his own 9 types of multiverses, which include quilted, inflationary, brane, cyclic, landscape, quantum, holographic, simulated, and ultimate multiverses. These classifications explore various dimensions of space, physical laws, and mathematical structures to explain the existence and interactions of multiple universes. One of the most intriguing aspects of the multiverse theory is its potential to explain the fine-tuning of our own universe for conscious life. The anthropic principle suggests that we exist in one of the few universes capable of supporting life. In this context, the multiverse provides an answer to why the physical constants of our universe are perfectly suited for life to evolve. If countless universes exist, each with different properties, it is not surprising that at least one has the necessary conditions for life as we know it. The multiverse theory also raises fascinating questions regarding the nature of reality and our place within it. Are we living in a universe that is merely one among many, each containing its own versions of events and outcomes? This notion has profound implications for our understanding of existence and the limits of human knowledge. Despite its allure, The multiverse theory faces significant criticism from the scientific community. A major challenge is its lack of empirical testability. Critics argue that, since we cannot observe or interact with other universes, the multiverse concept does not meet the necessary criteria of falsifiability to be considered a scientific hypothesis. Paul Davies, a prominent cosmologist, likens the multiverse to theological discussions, implying that it requires a leap of faith akin to belief in an unseen creator. Another respected physicist, George Ellis, points out that the multiverse is beyond the reach of our telescopes, making it potentially impossible to gather empirical evidence for its existence. He emphasizes the importance of observational testing in science and warns against accepting theories that lack empirical verification. In contrast, proponents like Max Tegmark argue that the multiverse is a simpler and more elegant explanation for the fine-tuning of our universe. They contend that rejecting the multiverse necessitates introducing unsupported processes and ad hoc postulates, making the single universe model more complex. The debate over the multiverse theory also extends into philosophical discussions regarding the nature of reality and existence. Modal realism, the belief that all possible worlds are as real as our own, aligns with the multiverse concept, suggesting that every conceivable scenario exists somewhere within the multiverse. This idea challenges traditional understandings of reality and raises profound questions about existence and the limits of human perception. Historically, the idea of multiple universes has appeared in various forms. In ancient times, philosophers like Democritus and Epicurus proposed the existence of countless worlds, each possessing unique characteristics. During the Middle Ages, the concept of multiple universes became more defined, though it remained largely speculative. In the 20th century, scientific discussions about the multiverse gained prominence. Theoretical physicists like Hugh Everett, with his many worlds interpretation of quantum mechanics, introduced the idea into modern science. According to the many worlds interpretation, every quantum event results in a branching universe, leading to an ever-expanding multiverse where all possible outcomes occur. The search for empirical evidence of the multiverse has been ongoing. In the 1990s, scientists like Stephen M. Feeney analyzed data from the Wilkinson Microwave Anisotropy Probe and claimed to find indications of collisions between our universe and parallel universes. However, subsequent analyses, including data from the Planck satellite, did not reveal any statistically significant evidence of such collisions. In 2015, astrophysicist Ranga Ramchari examined the cosmic radiation spectrum and discovered a signal that could potentially indicate the presence of a parallel universe. However, this finding remains debated, with a significant possibility that the signal is merely noise. Despite the lack of definitive evidence, the multiverse theory continues to captivate both scientists and the public. It provides an intriguing explanation for the mysteries of our universe and opens a realm of possibilities that challenge our understanding of reality. One of the most compelling arguments for the multiverse is its ability to explain the fine-tuning of our universe. The physical constants of our universe, such as the strength of gravity and the properties of fundamental particles, are precisely calibrated to allow for the existence of life. If any of these constants were even slightly different, life as we know it would not be possible. The multiverse offers a plausible explanation for this fine-tuning. If countless universes exist, each with different physical constants, it is not surprising that at least one universe has the right conditions for life. In this context, our existence is not the result of deliberate design, but rather the consequence of living in one of the few universes where life can emerge. The multiverse theory also intersects with other major scientific concepts, such as cosmic inflation and string theory. Cosmic inflation, the rapid expansion of the universe in its earliest moments, suggests that inflation did not end uniformly across the cosmos. Instead, it created distinct bubble universes, each with its own set of physical laws. String theory, a theoretical framework attempting to reconcile quantum mechanics and general relativity, also supports the idea of multiple universes. According to string theory, our universe is one of many branes floating in a higher dimensional space. These branes may interact, leading to the creation of new universes through collisions. While the multiverse theory provides a compelling explanation for various aspects of our universe, it also presents significant challenges. A major issue is the lack of direct evidence. Unlike other scientific theories that can be tested and validated through experimentation and observation, the multiverse remains largely speculative. The inability to empirically verify the existence of other universes has led some scientists to question whether the multiverse is a scientific hypothesis or merely a philosophical concept. Despite these challenges, the multiverse theory continues to inspire scientific inquiry and philosophical debate. It expands the boundaries of our understanding of reality and encourages us to consider the vastness of existence beyond our own universe. Whether or not we ever obtain empirical evidence for the multiverse, exploring this idea enriches our comprehension of the cosmos and our place within it. In conclusion, the multiverse theory suggests the existence of multiple universes with different physical laws and constants. While it remains a subject of debate and speculation, it provides a compelling explanation for the fine-tuning of our universe and challenges our understanding of reality. As we continue to explore the mysteries of the cosmos, the possibility of a multiverse broadens our perspectives and invites us to envision a universe far more extensive and complex than we currently comprehend. Though controversial, this theory has profound implications for our understanding of existence, offering a framework to examine questions about reality, the origins of the universe, and the potential for life beyond our own world. As scientific and philosophical endeavors progress, the multiverse remains a fascinating and thought-provoking concept that stretches the limits of human imagination and knowledge. The Benevolent Overlord hypothesis presents an intriguing scenario where advanced civilizations act as guardians or overseers of less developed civilizations, such as ours, subtly guiding our progress and protecting us from potential hostile extraterrestrial threats until we are prepared. This concept sparks the imagination, suggesting a universe abundant with life forms that may have taken upon themselves the responsibility of ensuring the safety and advancement of younger, less technologically developed species. To understand this hypothesis, we can consider the idea that advanced extraterrestrial civilizations could be more similar to us than we might expect. Research from the University of Oxford provides fascinating insights into this possibility. Scientists propose that aliens, like humans, might be shaped by evolutionary processes such as natural selection. This implies that despite potentially vast differences in biology and environment, extraterrestrial beings could share fundamental similarities with us, having evolved to become fitter and stronger over time. The Oxford study suggests that these advanced civilizations would have undergone major evolutionary transitions, similar to those seen on Earth. For instance, just as single cells evolved into complex multicellular organisms on our planet, alien species might have experienced comparable leaps in complexity. These transitions likely result in organisms with intricate parts functioning together, necessitating mechanisms to maintain cooperation and stability. Given this evolutionary perspective, it is reasonable to suggest that some of these advanced civilizations may develop a sense of duty toward emerging civilizations like ours. If they have undergone and overcome their own phases of vulnerability and growth, they may feel a sense of empathy toward younger species facing similar challenges. This empathy could translate into actions intended to guide and safeguard us, ensuring that we do not encounter hostile entities before we are capable of defending ourselves. We can all envision a galaxy where advanced beings quietly observe developing civilizations, stepping in only when necessary to prevent disastrous encounters with hostile extraterrestrials. These guardians might utilize advanced technologies to conceal their existence, subtly shaping the course of a civilization's progress. Their guidance could manifest in multiple ways, such as steering scientific advancements in a positive direction or mitigating potential dangers posed by other spacefaring species. One may question why these benevolent overseers would opt to remain hidden rather than directly engaging with us. The answer could lie in their appreciation of the significance of self-discovery and growth. Much like a parent guiding a child without dictating every action, these advanced civilizations may hold the belief that allowing us to experience our own successes and failures is essential to our development. By remaining in the background, They ensure that our progress is driven by our own efforts, maintaining the authenticity of our evolution. The findings of Oxford researchers lend support to the notion that if extraterrestrial life exists, it would likely be intricate and capable of exhibiting highly sophisticated behaviors. The mechanisms that sustain cooperation and order within these organisms could extend to their societal frameworks, promoting a culture of guardianship and oversight. This suggests that advanced civilizations may not only surpass us technologically, but also possess highly developed ethical frameworks that guide their interactions with less advanced species. In this context, the Benevolent Overlord hypothesis presents an optimistic take on the Fermi Paradox, which questions why we have yet to establish contact with extraterrestrial civilizations, despite the strong likelihood of their existence. Perhaps their silence and lack of direct engagement do not stem from an absence of life in the cosmos, but rather from a conscious decision by advanced beings to monitor and protect us from a distance. They may be waiting for the appropriate moment, ensuring that when contact eventually occurs, it happens under circumstances that are safe and beneficial for all parties involved. This hypothesis also introduces a range of possibilities regarding how we might eventually detect these guardians. As our own technology advances, we may acquire the capability to recognize the subtle influences and protective measures these civilizations have implemented. Such a discovery could radically transform our perception of our place in the universe, shifting our outlook from one of isolation to one of interconnectedness with a vast galactic community. Ultimately, the Benevolent Overlord hypothesis challenges us to contemplate the possibility that advanced civilizations act not as conquerors or indifferent spectators, but as custodians of the cosmos. It encourages us to envision a universe where compassion and stewardship advance alongside technological progress, where the wisdom of older species serves to foster the growth and development of younger ones. This vision of the future inspires us to gaze at the stars with hope, curiosity, and a profound sense of shared destiny with the countless forms of life that may exist across our galaxy.